let me minimize this. Hang on. Oh, I gotta move the window. How do you do that? Okay. And then if anybody's got any question or wanted me to go back a slide or something, just go ahead and say out loud because I'm gonna minimize. I'm not gonna see, oh, I can't do that yet. Darn it. See, now I can't even click, hang on. All right, got it under control. All right, I've got to share my screen first of all, right? Okay, there we go. Oh, I'm gonna ruin my first slide. Darn it. Okay. There we go. Okay. Now I gotta minimize all your lovely faces. Okay, everybody see that?
Yep.
Yes.
Okay. That's my only slap at religion through this whole thing, so I just had to put that there. And that wasn't like a joke or anything. It's not any kind of, like, no, an atheist didn't Photoshop that. It's like a serious thing. So like at the very end of the universe, it's like a guy. All right, the first strange celestial object is something in our own solar system, okay? And it's got the designation of 3753 Cruenia. Okay, and you may see some articles here and there from recent years saying like, is that a second moon?
It got really dark.
Okay, this is an artist rendering. This is not an actual image, and you'll soon find out why. Okay, and no, it's not really a second moon, but it is in sync with the Earth in kind of an odd way. All right, discovered in 1986. It is a near-Earth asteroid. Thankfully, it doesn't get too near to us. It's only 3 miles in diameter, so if it was the second moon, our regular moon is like 2,100, 2,150 miles in diameter, so this thing's tiny. Okay, and what's strange about it, it shares Earth's orbit, kind of. It's choreographed in a stable 364-day orbit around the sun. Doesn't get any closer than 8.5 million miles. It happens to be closest to Earth each November. And believe it or not, it is the subject of a proposed NASA mission. Okay, and this is a very two-dimensional kind of what you'd call an overhead review of, and it's a little deceiving because the orbit of Cruenia is tilted to the plane of our orbit, but you could see how it's kind of in sync, and that how once a year Earth kind of rendezvous with it, 8.5 million miles. That isn't very close. Okay, now this is kind of interesting. The orbit to us, this is what's called the stationary Earth view of its orbit. And it appears from our viewpoint to make like a kidney bean shaped orbit. And that's because of how it is basically in sync with us, but it dips up and above and below our plane of orbit.
It's going around.
And it's not real, okay, this just happens to be an observatory, but it's not, at 3 miles in diameter, it's not going to look like a heck of a lot, even through the Hubble telescope. All right, so another strange object in our own solar system, but we're going out to the outer part of the solar system, Haumea. And once again, this is not any kind of actual image. This is an artist rendering of Haumea. All right, so it was just discovered about 15 years ago. It's a Plutoid dwarf. It's about 900 miles in diameter, which compared to Pluto is about 1,450 miles in diameter. So it's a pretty good sized object. it's currently way out there, okay, as you'll see in one of the further slides, 50 astronomical units. So that's 50 times 93 million miles, quite far at this point. And albedo refers to surface brightness of an object, and it's got a very high surface brightness. All right, besides its odd shape, what's weird about Haumea? Well, it rotates faster than any known body in our solar system. The thing twirls around in less than 4 hours. And it's also kind of weird that this object has 2 moons, Hayaka and Namaka. It also has a ring. And okay, this is actually a graphic from one of those. Morgan might know the name of some of these kind of fly through space programs.
Celestia is the one that I've used.
Yeah.
I mean, there are different ones on the phone, but on the computer, I've used Celestia.
This might be from that or a very similar kind of a, obviously it's sped up quite a bit, the rotation, but gives you an idea what this object might look like. Okay, and its orbit. Okay, now the blue is the orbit of Neptune. And this graphic is pretty good. If you look up in the upper left, you can see the years. Okay, the orbit is 248 years was Pluto. I forgot what it was, but it's a very similar orbital period. See, right now it's way out there, way beyond the orbit of Neptune. Sinks below. Neptune's orbit is pretty much in the same plane as ours with respect to the sun and the rest of the planet except for Pluto and these other objects like Haumea.
By the way, if I can interject, it's one of the reasons why Pluto was booted as a planet.
It's too little?
No, not its size. They began questioning whether it was a planet because of its inclination to the ecliptic plane.
Oh, yeah.
It has an inclination that is more like that of a comet than a planet.
Yeah, as does this object here. And this is kind of cool. Like, how did we come to know that Haumea has the two little moons? Well, this is an image from back in 2008, or a series of images, I should say. And you can see from the counter at lower right, it's over the course of about 7 days or so. And it's from the Hubble Wide Field Camera number 2. And you can see little Namaka and Hayaka in orbit around Haumea. Okay, still in our own solar system. By the way, I could do another whole one of these because there's some the universe is full of just weird stuff. So Jupiter's moon Io, okay, old nasty gas station pizza. That's kind of what it looks like. All right, so it's discovered by Galileo, of course. It's one of the 4 Galilean moons that can be easily seen through just about any sort of amateur telescope, provided it's at least 15 power or so. Okay, and it's bigger than our moon. It's a good-sized object. It's also the most geologically active body that we know of in the entire solar system, over 400 active volcanoes, constant eruptions, plumes going way up from the surface. Really cold, of course, as is just about anything that's beyond the orbit of Mars. And it probably stinks because it's very sulfurous. It has mountains as high as Everest. And there's been some absolutely stunning pictures from the three main Jupiter probes. This is one from Galileo. It shows, and I believe this is in fully visible light too. A lot of these images, they do get, it's overlain. Sometimes there'll be a composite of several images, or they'll have it in somewhat false color to better show details. I'm pretty sure this one is an actual, just plain old visible light image from Galileo.
can't hear that without thinking about Queen.
What's that?
I can't hear Galileo without Bohemian Rhapsody.
Oh. It does have
never been able to.
ring to it, or yeah, it rolls off the tongue.
Yeah.
So this is an infrared image from taken by one of the, I can't remember which one, Voyager or Galileo. It shows, and keep in mind, it's a snapshot, shows all the eruptions that are going on Io at any given moment, even on its dark side.
Hey, Mark?
I'm wired to see that face.
Do you see that face
That
in
looks
the image?
Mercury.
Where?
Up in the upper left, those two bright yellow dots that are diagonal to, in a diagonal line. If you look at those and look at the surrounding area, that looks like a face there with the eye socket and a nose bridge
and a mustache. It has a mustache.
I can even see a lip and a very big bedded jaw.
You know, it's
and
funny.
Hair.
I can't see it. However, I was going to weave that pareidolia thing in because a long time ago, a part of the Eagle Nebula, part of it looked to me like Leon Trotsky. And I could not find the segment of the nebula. Anyway, I'm still not seeing it. So,
see Jess.
You see where your arrow is? You see where your cursor is? Move up, move the cursor up. Okay, that whole area right in there. A little bit above and mostly below where your cursor just was.
The shadow,
I see
shadow
it.
going like this is like the face and eye.
Right,
yeah.
Go a little lower than that, you'll get to the chin.
Where's the chin?
Too.
We're wired to see it.
See, he's wearing braces. Into a Walkman. I see it.
I usually pick up these because I'm weird. I see like.
Oh, I can do a virtual background.
Yeah, I don't know what you guys are drinking because I don't see it either.
All right. That's pretty cool, though. I'm glad you spotted that. But usually I spot those sort of things. So, okay, this is an image, I believe, from Juno. And shows even more detail and a bunch of eruptions happening on over the, what's it called? The horizon, I guess you'd say. Right on the other side of the horizon here, a bunch of eruptions happening. And this is from Juno. It's a much more of a close-up, and you can actually see some kind of lava-ish activity there off to the left, an eruption going on, and I've lost my cursor. And these things, I guess, would be just dark areas of formerly erupted sulfur dioxide and whatnot. All right, on to Saturn and its large moon Titan, okay, which is often speculated to be a possible second place for life in our solar system. And pretty much invisible light. This is what it's going to look like. This is, of course, a Cassini image. All right, it is the second largest moon in our solar system. And it is the only moon with a substantial atmosphere, like ours, mostly nitrogen, okay? But it only receives 1% of the sunlight we receive, so conditions are going to be quite different on Titan. But it does have clouds, rain, rivers, and whatnot, and seas of methane and ethane. It's got some big seas. I think the largest sea on Titan is about the size of the Caspian Sea. Which is a good size, okay? And strangely, it has all this precipitation and, clouds and rain of, hydrocarbons, but, it has, to our knowledge, a water ice crust, and below it is liquid water, which is just kind of a strange thing. All right, and Cassini was probably the most successful of all the missions. It continued to, transmit incredible amounts of data and spectacular images for a full like 10 years until they crashed it into Saturn. That was just about 2 years ago, if I remember correctly.
Oh, this is not quite on the same topic, but since you talk about the craft there, NASA just within the last week reestablished communications or contact with the Voyager spacecraft.
Oh,
Wow. And that's got to be, isn't it? It's obviously
It's outside of our solar system now.
okay.
It
Amazing.
our solar system a few years ago.
That is amazing. I had not seen or heard about that. That is spectacular. So Cassini's cameras were able to look through its atmospheric haze using different infrared and other techniques, and was able to give a good composite image of a lot of its surface features.
Hey, do you see that giant square on the surface?
Yes.
All right, so, and then radar imagery that Cassini used reveals the shapes and sizes of some of its seas, which are concentrated near its poles for whatever reason. I like the name of this one, Jingpo Lacus. This is very cool. So it's actual imagery of the Huygens probe, which Cassini released back in 2005 to land on Titan's surface. They always have kind of cheesy music to these things.
Royalty free.
oh.
And of course, little Huygens couldn't transmit data for too long, as cold as can be on the surface of Titan, unfortunately. So I don't know how long it continued to transmit images and data, but I don't think very long, at minus 200 degrees. All right, Saturn's strange polar hexagon. A lot of you have probably seen this one before. It's obviously enormous. You can fit several Earths in there. There's a kind of an enhanced color view of it from Cassini. Here's a enhanced color sort of series of images, and you can see kind of what's going on. There's a central cyclone thingy that rotates a heck of a lot faster than the rest of the storm, or whatever we want to call it. And this video gives a little explanation of what they don't really know exactly what, causes this hexagon, but this is one possible explanation.
Hexagons are the most efficient way for circles to pack together.
Good point.
This one is, I think, related to some symmetries of the top. Yeah, template.
At least this music's a little bit spacey. At least that was slightly better music. All right, before we leave the solar system, this is something I just kind of stuck in here a couple days ago, but it's very, very cool, okay? And this person, Drexler, makes all kind of videos like this. It's like, what would happen if somebody fell into Jupiter and stuff like that. But I thought this one was particularly good.
Sun, a giant hot ball that without we would never see the light of the day, as well as any life on Earth ever. So yeah, Sun has allowed us to live, but it is as well slowly killing us. We all know that the Sun will turn into a red giant 5 billion years from now, but it doesn't matter since the Sun will become so hot in a billion years that every ocean and water on Earth will evaporate, so no life will be possible without water. But that is still long off before we eventually either destroy ourselves and our planet or move on to another planet, moon, or even another star. So during this process of our sun dying, interesting things will happen to other planets and moons. So the sun will expand so much it is insane. So this is our current sun, and this is the maximum size it could reach when it becomes a red giant. This dot here is our current sun, and in this dot you can fit 1,300,000 Earths, and it is 1,400,000 kilometers in diameter. And when it becomes a red giant, it will be 300 million kilometers in diameter. Our sun will expand to the orbit of Earth and will swallow Mercury, Venus, and possibly Earth. But if it doesn't swallow Earth, it will become a hot hell world. But Mars will still be there, and it will be extremely hot. Sun would appear a few hundred times larger from even Mars. A cold place that is now will become a hell in future. Jupiter and its moons will as well be very hot. Jupiter's moon, Europa, will have its icy crust unfrozen, and it will have oceans flowing on its surface. It is as well possible that an atmosphere could be formed on Europa at that time, consisting of oxygen. It will be a hot oceanic moon. But here is the interesting part. Saturn will be in the habitable zone, and its cold moon Titan, that currently averages a temperature of minus 179 Celsius, will finally have a good temperature for human life and life in general. Liquid water could flow on Titan. Titan as well has an atmosphere, and has water underneath its surface. So when the sun becomes a red giant, humans could pump that water back onto the surface and we'll have water flowing through Titan. We could create oxygen with plants. Basically, we could transform Titan into being Earth-like very easily. So while we may have moved to another star at that point, there still could be humans in the solar system left. We could still thrive in our home system. Uranus and its moons will not be used for living since they are small and have low gravity, and they most likely will be used for mining out important resources and transporting them back to Titan. And Neptune will have no major moons left since Neptune will swallow its largest moon Triton or form it into a ring system. Pluto will turn its frozen nitrogen on the surface into liquid nitrogen, since nitrogen melts on minus 210 Celsius, but water would still be frozen. Still, it would have liquid nitrogen oceans flowing on its surface. So basically, almost every icy moon and dwarf planet will have liquid flowing through on their surface. Solar system will become a place of vast oceans. Our sun will completely change the solar system. We will probably populate every major moon of Saturn as well. And it will be like that for 3 billion years, until the sun reaches the terrible fate in 8 billion years from now of exploding and creating a big magnificent nebula. And humans and Titan will encounter that event, and suddenly the sun will start to cool down, and it will be just a dot of what it used to be. It would become a cold white dwarf. Suddenly, the hot oceanic moons will start freezing again. This is the deadline for humans and Titan. In case if we haven't found a solution to cope with these cold and harsh conditions, humans and Titan in 5 billion years will as well encounter a collision with Andromeda, meaning Milky Way and Andromeda will collide. So that means that humans and Titan will be in a completely new galaxy called Milkdromeda. In case we could somehow survive the unbearable cold, we yet have another deadline. That is in the next 30 trillion years. Yes, it is that far. So then the sun will collide with another star and potentially eject every planet out of its orbit. But it is possible that planets will somehow stay in orbit and Titan will stay in place. In that case, it has another quadrillion years. That is 1 with 15 zeros. Keep in mind, the universe exists for just 13.8 billion years. So that's quite some time. Yeah, in quadrillion years, over that time, sun will very slowly cool down and turn into a black dwarf, a completely cooled down star. Humans and Titan and another moons would have no energy sources left. That will be the beginning of the end of our home solar system. Every planet and moon we once knew will be left in the dark, floating.
Sounds okay.
Whoops, sorry. A quadrillion years. Okay, that's I can't even comprehend that.
No, I'm depressed. I'm going to need meds.
If you want to visualize that, imagine how long this year has felt and then double it.
Yep. Okay, now this is weird. I can't see my, now that doesn't make sense. Okay. No, we don't want that. Okay. I've lost my arrow. I lost my directional arrow. Why? Why?
You can see it.
I
think
see
it's
it
full screen now, that's why.
Oh, come on. You can see, oh, I got to get rid of this stupid thing. That's why. No. Oh, see, I made the video too big. Okay, hang on just a second. Escape. Okay, there we go. Oh, come on. Sorry. For some reason, my forward arrow isn't popping up. I got to hit escape twice. And it's still not there. There it is. Never mind. Whoops. Ow. All right. Sorry about that. Okay. On from our solar system out to our stellar neighborhood. Okay, some of you have heard of Barnard's star. Okay, this is its apparent motion to us over the course of 9 years. And this was taken by an amateur astronomer who periodically took images of the exact same region of sky over a period of time. That's how fast this thing is whizzing. So it is the fourth closest individual star, but keep in mind that Alpha Centauri, the nearest star, is a triple system. So, and it's a red dwarf. It's much, much older than our own sun. And as this image can show you, it's got the highest, what we call proper motion of any known star. The proper motion is basically our apparent, how far it moves with respect to the background stars, which would be much, much farther away, how much it moves per year. And that corresponds to a relative motion of 60 miles per second, which, and 100 miles per second would be its true velocity through space when all the trigonometry and whatnot is done. And it's gonna be our closest star, almost be our closest star, 9,000 years from now, almost 10,000 years from now. All right, it's been confirmed to have a super Earth, a cold super Earth, rocky planet that's about 3 times the mass of our planet. And this is just a diagram showing the size of Barnard's star really isn't that much bigger than our planet Jupiter. This is an artist's conception of what this cold super Earth might look like orbiting Barnard's star. All right, Eta Carinae. Good thing it's not closer. All right, so what this is, and it's extremely luminous and massive double star system that happens to be extremely active. These two massive stars have a combined luminosity. The two stars combined have a luminosity of 5 million suns. Star 1 is 125 times more massive as the sun, and star 2 is 30 times more massive. Star number 1 is expected to go supernova very soon. Now, astronomically speaking, that could mean in 2,000 years. It could mean in 10 years. We really don't know. So what these two lobes are, okay, it's called the homunculus nebula. So it's material that was started to be ejected during what they called Eta Carinae's great eruption. And astronomers think this occurred 150 years ago from our perspective. But keep in mind, this thing is the talking, okay, I can get rid of that.
Come here, boy. Come here.
So 150 years ago from our perspective, but actually it started blowing up 7,950 years ago approximately, because it's quite different. But it's a good thing because an event like this that would be more in our stellar neighborhood, and if the dispersal of energy was right in our so-called line of sight, such an explosion could strip away our ozone layer or fry us with gamma rays or something horrible. So what's really interesting about this, other than it's like sheer power and what's going on, they think astrophysicists and astronomers now think that it's due to 3 stars being locked in a kind of tango battle. And one star ended up getting devoured. And here is a little animation of what they think happened. Here comes the interloper. It somehow caused this huge transfer of energy. And that star, which was the big one, gets flung out of the stellar system. And the interloper, and then here comes the one that was flung out again. Bizarre, but that is the model that they think constitutes what happened with this object. And so, yeah, the little guy is, who was the big guy, is still back and kind of in orbit of the system. That is just one strange object. Whoops. All right, so, and the Carina Nebula is, you know, we can't really see this here. Maybe from the, no, I don't even think from the southern tip of Florida. This is a southern hemisphere object, but it's a absolutely beautiful part of the Milky Way as far as nebulosity. And this, of course, is probably enhanced color, but there have been some fantastic astrophotos of this nebula just from, you know, amateur telescopes and whatnot. Absolutely beautiful. And Eta Carinae is somewhere at its center here. Okay, on to a star known as VY, which is a designation for variable stars within a constellation. And this happens to be VY because it was probably it seems like it wouldn't be because, you know, like, so the first variable star discovered in the constellation Canis Majoris would be AA, I guess, but strangely enough, well, I don't want to get too ahead of myself.
I think that V stands for variable.
What's that?
That V stands for variable.
Maybe, I don't know, but some of the other variable stars will be like RR, you know, constellation. I'm not quite sure about that. But anyway, it's an absolute behemoth of a star. And so they call this a red hypergiant. It's either the largest star that we know of or the second largest, because there's another star, this one's UV Scuti. Scutum is a summer constellation. And there's a similar star. We don't really know which one's more massive. So its diameter is 1,400 times that of our sun, but the mass is a mere 17 suns. Why? Because it's a big, vacuous, extremely bright and luminous and powerful, but not all that massive red hypergiant. It's most of its atmosphere is pretty close to a vacuum. So it's so huge that if it was replacing our sun, it would pretty much engulf Saturn's orbit just about. That's how huge it is. And despite it being not very massive at all, it has the luminosity of at least 300,000 of our suns. So yeah, that's how, like I said, it's almost like a vacuum. VY Canis Majoris has 100,000 times less dense than our own atmosphere, which is just very strange. And here's a little diagram that basically shows the size of the sun with a section of VY Canis Majoris and compares our entire orbit with the size of this star, and it's enormous. And you can see this thing probably, well, not tonight because it's very, very cloudy, but look to the southern sky. If you could see Sirius, the brightest star in the sky, and you have any kind of app on your phone or whatnot that shows the constellations, it's located right above what would be the dog's tail, would be to the lower right of the star Sirius. And it's visible in binoculars, but it is a variable star. It varies from about magnitude 6.5, which in absolute dark desert skies would be about the limit of naked eye, but it varies down to ninth magnitude, which is more like, you know, the limit of your average pair of binoculars. Okay, now this particular video or animation has been seen in many different forms. This one is a little bit different.
How do I turn it off? Oh, we did. I don't see him.
I guess they're trying to say it's seriously big.
Yeah.
Ha, 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 ha. Serious? To get
Finally.
I don't think they sent them, Randy.
What?
They didn't send them.
They didn't?
Nah. I'm trying to figure out how to turn off the camera so I can eat.
Okay, Susan, down in the lower left, you can mute your, by clicking on that speaker.
It mutes my microphone. I'm trying to.
This
There
is
should be a
the,
mute button for the microphone, but also a stop camera button for the
this
video.
is the crazy part here. It would take us 1,100 years just to circle it once. That's how big this thing is. I definitely see something in there. Anyway. All right. So PSR J0952, very tiny but super dense object, okay? And details forthcoming. It is a star. It's called a millisecond pulsar. A pulsar is also known as a neutron star because it's pretty much, well, this is a description. Why do they call it a millisecond pulsar? Because it spins, the thing rotates at 707 times per second. It's approximately 1.4 times the mass of our own sun. However, it's only 12 to 15 miles in diameter. Its material is so dense that 1 teaspoon of its material would weigh 1 billion tons on Earth. So it's called what's known as a black widow pulsar. It shares material from its own companion star. And I believe that this is, okay, it's an artist's representation of it gravitationally shearing this material from its companion. And so, can I pause this? Okay, so what is a pulsar? Okay, it's just, you know, basically a bulk of it is just compressed neutrons. they don't even really know what's at the core of these things. Everything's so super compressed. But basically what it is one type of dead star. I mean, it's not quite dead because it's still incredibly active. So it was a kind of an informative short video.
A neutron star is the densest body we know of in astrophysics, besides a black hole. If you somehow had a little stone-sized piece of neutron star matter, it would weigh 100 million metric tons, and it would immediately fall right through your hand.
Because the neutron star is so dense, it generates an intense gravitational field.
It is really hard to exaggerate how dramatic and dangerous a neutron star is. The gravity is so intense, it would actually bend light around it. You would see all these kind of weird shimmering effects.
Dazzling, but deadly. No astronaut will ever be able to approach a neutron star. But if you're an armchair traveler and want to find out what would happen, let's send a galactic crash test dummy. We'll call him Chuck. As Chuck nears the neutron star, its gravitational grip is doing very bad things.
The gravity is pulling on him so hard that he is accelerating all the way down to the surface. He'll be moving at very roughly 1/2 to 2/3 of the speed of light.
The neutron star's gravity is 200 billion times stronger than on Earth. Around 150 miles above the surface, it starts to pull on Chuck's limbs in a distinctly unpleasant way.
As you get closer and closer to a neutron star, we were told to think that it would be this elegant spaghettification where you would get longer like a piece of spaghetti. But in reality, you're going to get ripped to shreds.
Think about what you're really going to experience. Think about, first, all your joints dislocated in your body. Your skin getting ripped off your body, your bones being pulled apart, your organs being pulled apart.
Hi, baby.
With a blink of an eye, our dummy is just a thin stream of atoms hurtling towards the star.
Those atoms will eventually fall down onto the neutron star. And unfortunately, the violence doesn't stop there.
What's left of Chuck hits the surface, triggering a huge burst of energy.
So we're talking about 100,000 miles per second. That's an impact. He's going to hit so hard that the amount of energy released is just huge. It would completely dwarf the entire arsenal of nuclear weapons on our planet.
Anything and anyone that ventures too close to a neutron star is destined for this catastrophic end.
In reality, it'd probably be, I'm imagining it'd be almost impossible to approach closer, you know, even remotely close anyway, because of the intense radiation that's most likely coming from these things. Okay, where's my arrow? Oh, come on. Okay. All right. Sorry about that. All right. The Cat's Eye Nebula, a psychedelic dying star. This is a visible light image from Hubble. Looks like a rotifer or something. They call this a planetary nebula, and this particular object is it's pretty much easily visible in a decent backyard scope. Doesn't look like this, of course. Just kind of looks like an elongated cloudy spot. You may be able to glimpse the central star of this nebula, which is the dying star that we're talking about here, that's shedding off all its layers. And of course, our sun will do something similar. But this one just happens to be, from our vantage point, just looks very, very strange. So, I mean, it's pretty long. It's a large object, obviously, at 1.17 trillion miles long. And this would be in the northern sky in the constellation of Draco, but it's very hard to, maybe with an app, you know, like I mentioned before, like a phone app that shows the deep sky objects superimposed on the constellations, might be able to sweep it up with a amateur telescope. It's just sort of hard to locate. The constellation Draco is very close to the Big Dipper and the Little Dipper, but there's really no bright stars to use as jumping off points. I was never able to sweep this one up. And of course, I don't have if you have a nice telescope with an equatorial mountain, computerized star finder and stuff, you're good to go. I just try to sweep things up. There's a refracting telescope on a regular camera mount. And I do what's called star hopping to locate these objects. So, yeah, I think they think what made these concentric rings is that the star is ejecting its mass in pulses, 1,500-year intervals. So, and each one of these dust shells, these concentric rings, contain as much mass as all of the planets in our solar system combined. And this is an ultraviolet image from Hubble of the Cat's Eye Nebula. All right, so the Boomerang Nebula. It's the coldest known place in space. It's also well, they call it a proto-planetary nebula. I think it's just, the star is just in the process of beginning to violently eject its outer layers. Why is it so cold? It's like, I think 1 degree above absolute, it's colder than space. Because this thing is ejecting, the flow of gas being ejected from the star is so rapid. It's 10 times what is considered to be normal speed for these things, that it just gets cooled in the process. And it's interesting how they were able to take its temperatures by just, examining how it absorbs the background, the cosmic background radiation, which is, for all practical purposes, a uniform 2.8 Kelvin. And so I believe it's one degree less than 1 degree Kelvin. No, it's less than that though. So, and this is an image from the Atacama Large Millimeter Submillimeter radio telescope array, and it shows the more detail in the ejections of this material. All right, some of you have seen this before, and some religious entities kind of took this real seriously. The Hand of God Nebula. So the designation is actually the name of the pulsar that's associated with this nebula. And as we saw before with the neutron star / pulsar, so it's the remain of like our sun is going to expand, blow up, but not explode. It doesn't have enough mass to explode. It's going to blow up to a red giant and then collapse, shed off a bunch of stuff, make the planetary nebula and everything, but it's going to shrink and remain as a white dwarf.
Mark?
Yes.
A better word for what you're trying to describe, because I know how easy it is to fall into that thing about blowing up or exploding. It's going to expand.
Expand, correct.
Expand because the pressure that'll be exerted from the inside of the star will be greater than the gravitational collapse, and that pressure will push the star's matter outward.
Exactly, and that's what our sun will expand, not actually explode. Now, a more massive star, I think the limit for an actual explosion, nova, is it has to be at least 3 point something times as big as the sun, as massive as the sun. So this was the remaining. Why is there a pulsar, here? Because it was a giant star that went supernova 1,700 of our years ago. Okay, once again, this thing's 17,000 light years distant, so it was actually went supernova more than 17,000 years ago. And it's not anywhere near as big as the one we just looked at, the Cat's Eye Nebula. This one's only about 150 years across, light years across at this point. And it has a pulsar in the center there. It rotates at only 7 times per second, as opposed to that millisecond pulsar, which was 707 times per second. And it just spews the energy out into space to create the complex structure that happens to look like a hand. And like I said, unsurprisingly, many religious entities seized on that one. This is in, I believe, it's a composite image of ultraviolet, infrared, and visible light. Yeah.
Also,
okay.
Mark, that it has that shape only because of the angle at which if you were to move that camera to a different angle, you wouldn't see that same shape.
Exactly. So probably from, Alpha Centauri, a nearby star, would look about the same because of the great distance. The nearest star is 4 light years away, where this thing is 1,700 or 17,000 light years away. So, but somewhere outside of our own stellar neighborhood, it's not going to look the same at all.
It might just look like the finger of God, is what you're saying?
Yeah. So, and this is just sort of an animation of how they take different images and different types of different wavelengths and how it looks. That's what it looks like in infrared, optical and X-ray, and the detail. So that was X-ray. Sorry, I said ultraviolet before. And the different, examining these objects in different wavelengths bring out different details. Whoops, I already played that, okay. Oh, that's how I do it, okay. And this is hey, Rafik, are you there? Rafik RSVP'd, we haven't seen him for a while, but he made this of, if you remember, a former governor of Texas, Rick Perry, who I think ran for president back in like 2012 or something. He fashioned this hand of, and he's a real holy guy.
He served as Trump's Secretary of the Department of Energy.
Is he?
Well, I don't know if he is now, but he did early in Trump's presidency.
And so quite a number of years, it was probably like 7 or 8 years ago, I posted this on our mail, because this was actually a photo of him he was robocalling Texans to join this big prayer rally at, I forget what Houston's big stadium is called. And this was the actual picture. It's like, he's supposed to be looking up at God. So Rafik sent it back and he photoshopped the hand of God in there. All right, so another weird designation. Okay, of course, some of the brighter deep sky objects, for some of you that know some stuff about amateur astronomy, like a certain galaxy you could see easily with a backyard telescope, will be Messier 82 or something. But they run out, those end at about 106. So then they have the New Galactic Catalog, NGC. And that only goes to 4 digits, I believe. So there's no NGC 10,000. It just ends at NGC 9999. So they come up with these different designations, different astronomical, astrophysical entities. So anyway, this is the nebula OH231.84 plus. And that's its declination and right ascension. I think that's what the numbers mean. And this is kind of what it looks like. And why is it smelly? Oh, they also call this the Calabash Nebula. Well, it was renamed the Rotten Egg Nebula because it's found to have a large amount of sulfur in it, which is kind of unusual. They call this a protoplanetary nebula, very similar thing. The star is just beginning to spew out its layers. So what we're seeing here is a dying red giant star blowing off its outer layers, which is what our sun's going to do. And it's beginning its transformation into a planetary nebula and white dwarf star, which once again our own sun will do. And this stuff's being ejected at, it's measured at 621,000 miles an hour. So that's pretty powerful. All right, here's two objects just because they're very beautiful. So it's NGC 6302, which is, I believe they call it the Butterfly Nebula, and Able 33, which is called the Diamond Ring Nebula. It's actually a planetary nebula. This is the star that died in the middle, but there happens to be a foreground star that makes it really, really pretty. All right, M82, formerly known as the Exploding Galaxy, because as I used to think it was a galaxy literally in the process of exploding. It's an object that is quite easily seen with backyard telescopes. Doesn't look quite like this though, but it does, the cigar elongated shape is easily visible. Hey, wait a minute, that's supposed to be an animation. Oh, okay, I think it's just another image of it. Oh, no, okay. Yeah, easily visible in backyard scopes under reasonably dark skies. I've seen it from my backyard here. So basically what it is an edge-on spiral galaxy like our own. 12 million light years away, 37,000,000 light years long, which is smaller. It's about a little more than a third the size of our galaxy. They call this a starburst region, all this red stuff and whatnot being ejected from the center. And what it is just tremendous outbursts of energy because stars are being born 10 times faster than stars that we've measured in our home galaxy, as far as we can measure this process happening. And they think that this intense star forming, I gotta back up just a minute. And one question is why, back to that star, VU Canis Majoris, like why are some stars so, humongous? And, why are some smaller like our sun? Well, in VY Canis Majoris' case, it's because it's already blown up to a red giant. But there are many, many stars that are vastly more, they're blue supergiants that aren't in any kind of end stage or anything that are super, super massive. And I think it's basically because there's more material in whatever stellar clouds that these stars are born in. And, our own sun was born in some kind of, nebula cloud long since dispersed, or the matter has coalesced into solid objects like our own planet and the sun itself. But they think that its companion galaxy, M81, which is also quite easy to pick out in backyard scopes, it's what's triggering all this activity. So ARP, which is yet another designation for deep sky objects, ARP 148, an object for the dirty-minded. What we have here, what do we have here? We have galaxies in an actual state of collision, 450 million light years from us. So they actually, this one probably went all the way through it already. Don't forget, we're seeing it as it was when during that wouldn't be the Cambrian, it would be the Ordovician area when this was a the very spot we're sitting on now was located under a shallow saltwater sea, and there was no land life. So we're seeing it as it was at that time. So this thing has probably gone all the way through, and I don't know if anything would happen to this or not. The strange thing about galactic collisions, you see all this glow and you think, oh, sure, there's going to be probably some collision, especially of gaseous material. But despite the way it looks, the distances between the stars are actually quite far. So would there be any kind of cataclysm? Well, maybe, but not so much by smaller objects colliding with each other. It would be more the gravitational and tidal forces of this one being pulled through this one. And this one could be, totally distorted or something. Different things seem to be happening to different galaxies that we observe in this sort of state.
Mark?
Yes.
What kind of time frame are you talking about for these events, like the collision of galaxies, or?
Well, you heard the man in the Drexler. You heard Drexler. Andromeda, and I think go back a couple of years when we were all going to meetups down to the museum when they had those wonderful astronomy and cosmology programs every month. There was a couple that referenced the Andromeda galaxy colliding with us, and that's going to be in, well, I don't have the raw figure, but let's put it this way, it's pretty far away still. It's naked eye visibility on a dark night, but the Andromeda galaxy is going to collide with ours in 2.4 billion years. So,
but how long does it take for two galaxies to collide?
Millions of years. This would probably take millions of years to pass all the way through. Yeah.
Okay.
Yeah.
Once it sort of passes through, it's not really strictly a pass, because what happens in a galaxy is that there's also partial merger, and both galaxies greatly distorted. They end up changing shape almost entirely. In fact, one of the class of galaxies called the elliptical galaxies, which is one of the main classes of types of galaxies. The elliptical galaxies are what result from galactic collisions.
Yeah, it could very well be. And back to that Drexler thing, apparently, they think ours is going to kind of more like merge with Andromeda. Called it Milkdromeda or something. But yeah, these things, it takes a while for these things to happen, but they are whizzing through space. And, we're getting kind of close to the end of the PowerPoint here, but I have something that references that.
So it would take a long time to pass through Uranus, is what you're saying.
Most likely, yes, indeed. So,
and along the way, you have to pick off all the Klingons.
Of course, thankfully. So yeah, they think this is actually a pretty good snapshot of an ongoing collision. All right, we're still in extragalactic, meaning outside of our own galaxy. Centaurus A, otherwise known as NGC 5128. I had the pleasure of seeing this object back in 1989. It was down in the Florida Keys, and it's a southern hemisphere object, but it was far enough above the horizon and out over the ocean, which was nice, very dark sky. I was able to see it through the telescope, modest telescope, a 4-inch Schmidt Cassegrain telescope. Didn't look like this. It looked more like a round object, but I could clearly see this dust lane. So the exact nature of it has been a kind of a mystery until recently. We think we got it figured out. It is an intense source of radio waves. So it is now considered to be the part of a large elliptical galaxy combining with a smaller spiral like ours. And strong source of X-rays and radio waves. I think it's one of the strongest sources of X-rays in the sky.
You guys.
And
why it looks like an X.
yeah, and it's supermassive black hole at the center of these objects. They think is the source of the intense X-rays, because they're pretty sure that the black hole at the center of this thing is 55 million times the mass of the sun, and that is just massive.
That's somewhere in the order of 10 times the mass of the black hole that's thought to be at the center of our galaxy.
Yep, that is correct. It is. Did I reference that? Oh yeah. Oh yeah. Yeah, you're fairly close there. Yeah, our own black hole at the center of the Milky Way is about 4 million times the mass of the sun. And this is more like a visible light object, or view, I should say. And of course, through my modest scope, I didn't see anything like that, but I did clearly see the circular and the dust lane going through it. No detail. I wasn't able to see any detail. Whereas the prior image, it would be once again a combination of visible light and probably infrared or ultraviolet, which is going to bring out more details.
Can I interrupt with another question?
Certainly.
If most galaxies have black holes at the center, then when they collide, how much of the galaxy gets sucked up into those black holes?
It would probably depend how close the two black holes themselves pass to one another. Like I said before, now towards the center even of our own galaxy, the stars do get a lot more densely packed.
Wow.
So, you probably would, if the centers of the two galaxies actually collide with one another, you could have some massive cataclysmic stuff going on besides just maybe the destruction of the form of shape of one galaxy. But otherwise, there's a lot of space between the stars. You'd have, once again, a lot of, our own Milky Way is full of dust and gas too. You'd probably have more collision of dust and gas than you would actual stars, actual objects colliding with one another. So yet another crazy designation, ULAS J1312, blah, blah. Once again, this has something to do with the declination and right ascension of position of the object in our own sky with reference to our reference point. So this thing is very old, very distant, and extremely powerful. This is an artist's conception. No photo, we can't photograph this thing like this. That's for darn sure. What the heck is it? Well, it's a quasar, okay? And it's the oldest and most distant one ever detected. Quasars are still a bit mysterious, even though we've designated space objects as, where'd my cursor go? There it is. We've designated certain objects as quasars since at least the 50s or 60s. So the light output of this thing is equal to 40 billion suns, okay? That's like immensely powerful. It's like indescribably powerful. Once again, these black holes are responsible for, these enormous emanations of energy, and they are fairly sure that the black hole associated with this quasar has a mass of 800 million suns, which obviously dwarfs that last object we looked at. That is one immense black hole.
Glad to be done with your abstract art class.
Now keep in mind, all our studies of this object, we detect this at 13.1 billion light years away. So we're seeing it and measuring it and collecting data on it as it was 13.1 billion years in the past. You're talking about, you know, not that far from the origin, our what is believed to be the very origin of our universe itself, which is more like 13.8 billion light years. So, and here's the crazy thing. What they call the co-moving distance is the actual distance they think this thing has moved from us or we've moved from them due to the expansion of the universe. The true distance from us at this point would be 29.36 billion light years.
What's the deal with the power?
What's that? Oh, was that a question? Right? Was that Ray?
Oh, no, sorry.
Oh, okay. So yeah, this thing is really powerful and really old and super duper bright. What does it look like right now? Hard to say because we'll never be able to see. So I referenced before, you know, a little later on something about space speed. So at approximately 40 north latitude, any given point on Earth moves at 771 miles an hour. And that's just the point going around the Earth, so to speak, every day. It also revolves around the sun, and we're moving in that fashion, the entire planet is, at 18.5 miles per second. So we're getting a little bit faster there. So keep in mind, right at this very moment, we're whizzing, where we sit is whizzing around the globe, so to speak, at 771. We're whizzing around the sun at 18.5 miles per second. So the sun itself has a motion. It's like its own motion, okay? What set it in motion? Well, we don't really know, but it's probably just the relationship to its own formation and the nearby stars and other stars that perhaps a billion years ago had a close approach and whizzed out in another direction. But it's got its own space motion pulling us and all the other planets with it towards the general direction of Vega, which is a bright star that we all know from the movie Contact, but it's also nearly overhead in the early evening of any clear summer evening. So it's hurtling in that direction at 12 miles per second. So we already got like 3 different motions that we're going through that are quite fast. However, the Milky Way itself rotates once every 225 million years. So it's rotated one complete time since like the days of like, well, the early Jurassic period, I guess, when Allosaurus and Brontosaurus were roaming the Earth. So our sun is also moving, whizzing around the center of the galaxy at 135 miles per second. So if all that isn't dizzying enough, our galaxy itself is whizzing through space at an estimated 361 miles per second, okay? That equates to going from Cleveland to LA in 7 seconds. That's how fast that is. And I'm gonna end with just I don't know, it's just a nice picture of a nebula. It's kind of ghostly. I didn't even note the designation of this object. I just thought the picture was kind of beautiful. And that is pretty much the presentation. So I'm going to stop sharing. Unless does anybody need me to go back to a different slide, a particular slide or anything?
No, but I did want to add one thing when you said the 225 million years period and mentioned Jurassic. That's actually the Triassic period.
Okay, so it was even before the Jurassic. So it was the days of I can't think of a Triassic dinosaur. Oh, Plateosaurus, the one that kind of looked like a Brontosaurus, but stood on its hind legs, but still had the long back.
we have a Triassic dinosaur in the museum. The small dinosaur that's sort of tucked away near the rear of Kirtland Hall. Oftentimes, it's in a little green case called Coelophysis.
That's Triassic?
That's a Triassic age dinosaur.
Weren't there more crocodilians that were?
Hey, Mike. Sorry, hey, Mark.
Around at that time.
Can you play the song that I sent on the YouTube?
Hang on just 1 minute. Let Valerie, what was your question?
No, weren't there more like crocodilians around that time, or it was earlier?
The Triassic? I think so.
It's like this.
Crocodilians existed during that time, but what we call crocodilians also coexisted with the earliest of the dinosaurs.
Right. They're a different branch, but they also evolved in kind of like their own different ways. They weren't just, they didn't just look like alligators and crocodiles of today, but they were kind of like their own.
No, you would,
category.
if you were to look at a crocodile from the Triassic, sitting right next to a modern day crocodile, you would see some similarities, but you would also notice some significant differences.
Right, exactly.
One of them is in size. The largest crocodiles of today don't even come close to basically the average size or the largest size of what we would call crocodilians of the Triassic.
It was kind of like a convergent evolution, or the convergent evolution, where the crocodilians of eons ago evolved into all these different shapes and forms, similar to the dinosaurs.
Sadesh, was that you asking a question?
No, it was not a question. Like, I sent a YouTube link. Can you play it for all of us? Like, it will be fun. It's related to your link.
I didn't quite understand. What was that?
I sent a link in the chat. I can check it out.
Oh, okay. You know what? I'm going to exit my screen here. I could always re-up it if somebody needs to see something again. Okay.
Yeah, maybe you can share it to everyone.
Oh, the link?
Yeah.
Oh, okay. Yeah, I think I know it. Okay, yeah.
Whenever life gets you down, Mrs. Brown.
Okay. Yeah, that's a good one. Okay, I'm going to share my screen again. Let's see. Okay.
Mark?
Yes.
One of the last screens you put up showed the speeds of different objects.
Yes.
From the Earth to the Milky Way.
Yeah, basically everything that relates to our planet.
So when you talk about the speed of the Milky Way, what's that in reference to?
Any given point, outside of the Milky Way, you know what I'm saying? If you were an observer on one of the satellite galaxies from the Milky Way, okay?
Yeah.
Which the Milky Way has several satellite galaxies, which are probably, orbiting the Milky Way themselves. But if you were a stationary observer on, say, a planet on a star in one of those companion dwarf galaxies to the Milky Way, that is what it's in reference to any fixed point in space.
It could also be in reference to the microwave background radiation.
Can that be considered stationary?
They can extrapolate the velocity. Yeah, that kind of makes sense. Now the mechanics of that, I cannot even begin to describe, but I can kind of understand what he's getting at. So.
But one question about the microwave background radiation, if that can be considered a stationary point of reference, does that go against what Einstein said, that there is no preferred frame of reference?
Well, it's literally every direction we look out in space. So it's kind of like the framework isn't the right word. You know what I'm saying? That's how they discovered it was what it is, at least according to all we know scientifically, because it's virtually the same in every direction.
But then it constitutes a preferred frame of reference.
Well, my understanding is that they actually have to subtract the motion of the Earth, which is mainly, I guess, the motion of our galaxy. It's a dipole bias in the measurement of the microwave background. So we actually are moving, as I understand it, with respect to the microwave background radiation. And that needs actually to be subtracted from the data in order to get the uniform microwave background. Randy, do you?
The microwave background radiation also. Okay, and help me out here, Rich, if I'm screwing this up. For those of you who don't know, Rich is actually a physicist.
Oh, excellent.
He knows quite a lot about this stuff. But anyways, keep in mind that it wouldn't be appropriate or correct to describe the background radiation as a fixed point, because the background radiation permeates all of space. So you're going to detect that radiation no matter what point in the sky you point your observing instrument, you're going to detect that radiation. So it's not in a single fixed point.
But it's the same everywhere, right?
Essentially,
not
yes.
Actually. I mean,
not. It's right. Not entirely. There's what you and I would consider minute variations.
No, but there's actually more than that. There's a bias. If you look at the microwave background radiation, there is a certain direction in space where it's great. It's a higher temperature, and another direction opposite that's a lower temperature. It's called the dipole anisotropy. And that actually is interpreted as the proper motion of us as observers against what is essentially a fixed background. But it does not, and I can't explain why, it does not violate general relativity.
So what would be the speed of the Earth relative to the microwave background radiation?
I suspect that the number he gave for the speed of the galaxy, that's pretty much what that is.
Because the other motions are all in other directions, but like the amount of, okay, so what was the sun is moving sort of in its own direction at, I forgot what it was, 18 miles a second. I forgot the number, but that dwarfs kind of, it's still.
Mark, all we can see is your forehead.
Oh, well, I'm about to show,
I thought it was a picture of another planet. I'm sorry.
I was about to show the link that Sadesh wanted us to show.
Oh, I'm sorry. Well,
that's okay. That's okay. I didn't even realize the camera. Okay, never mind. Now I gotta get out of it.
I forget, what was the speed of the galaxy?
320. Okay, you know what? I'm gonna let me show Sadesh's.
Yeah.
It's really, really fast.
Yeah. Okay, yeah, it's pretty fast. Yeah, you're right. Okay, hang on a second. Share. There we go. Okay. Here we go. Okay.
And things seem hard or tough.
Oh, gotta go back to the beginning.
Whenever life gets you down, Mrs. Brown, and things seem hard or tough.
The answer might be in here, Dale.
People are stupid, obnoxious, or daft. And you feel that you ain't quite enough. Just remember that you're standing on a planet that's revolving at 900 miles an hour. It's orbiting at 90 miles a second, so it's reckoned a sun that is the source of all our power. The sun and you and me and all the stars that we can see are moving at 1 million miles a day in an outer spiral arm at 40,000 miles an hour of the galaxy we call the Milky Way. Our galaxy itself contains 100 billion stars. It's 100,000 light years side to side. It bulges in the middle, 16,000 light years thick, but out by us it's just 3,000 light years wide. We're 30,000 light years from galactic central point. We go round every 200 million years. And our galaxy is only one of millions of billions in this amazing and expanding universe. On expanding and expanding in all of the directions it can whiz, as fast as it can go, the speed of light, 12 million miles a minute, and that's the fastest speed there is. So remember, when you're feeling very small and insecure, how amazingly unlikely is your birth, and pray that there's intelligent life somewhere up in space, 'cause there's bugger all down here on Earth.
That was not Stephen Hawking.
That wasn't, but yeah, that's Monty Python. Yeah.
Does anybody check the accuracy of that song?
Well, okay, so I gave a figure of 717. Now, don't forget, strangely enough, different points on our globe are going to rotate at different speeds. Strangely enough.
Yeah.
So point on the equator, they said 900.
Yeah.
900 miles an hour. That's probably at the equator, so
yes.
Technically correct. At our point on the globe, it's 717 miles an hour.
Yes.
That concept kind of freaks me out, actually.
Hey, Mark, I had a quick question, Mark. Did you have a slide on dark matter?
No, I did not, and that is a topic for like a whole nother presentation that I'm hoping I can get. See, I have like no credentials. I'm not a scientist. But I know somebody who could probably give us a pretty good presentation on that very topic. That topic is worth an entire thing in itself.
You should have said you did have one and she couldn't see it.
Okay, I came late, so I thought I missed it, because but thank you for the presentation. Really appreciate it.
Oh, thanks. I'm glad you enjoyed it. Yeah, dark matter. Actually, Mono Singham gave us one on. Did he give us a dark matter, Dale or Brandy? Do you remember?
No,
we had that at the museum.
I think he referenced dark matter, but he's never given us kind of a full-blown presentation on it. Not that I remember.
I could have sworn like it might have been a CFI thing. Yeah, I know there was one down at the museum for sure. Probably multiple ones, or maybe I got somebody else in for a CFI thing. But I will bet you that Mono can give us, even though he's a theoretical physicist as opposed to an astrophysicist, but he would be able to give us a very good presentation on dark matter and dark energy, for that matter.
But that song didn't quite go up to the motion of the galaxy itself.
Yeah, it gave it in miles per hour. I gave it in miles per second.
But that was the motion of the outer rim of the galaxy relative to the center of the galaxy.
Okay, good point. Once again, just like the points on our globe, so where you're sitting is rotating at 717 miles per hour. The point on the equator might be 900 miles an hour.
Well, you scientists always seem to find a way to justify this stuff. Oh my God.
You're going to have the same thing in the galaxy. Why? Because we're kind of towards the outer edge, but not all the way out.
But what's the motion of the galaxy itself relative to the background radiation?
That would be what is measured. That would be those figures.
No, that's two different things.
No, it isn't. One's in miles per hour and one's in...
No, that's not what I mean.
What Dale is asking is two different things.
The galaxy is rotating, so there's a speed relative to the center of the galaxy, but then the whole galaxy itself is moving relative to the microwave background radiation.
Think in terms of we're moving, we in the Andromeda galaxy are moving towards each other. So at what speed are we moving? Is the whole galaxy itself moving through space towards Andromeda galaxy?
Good question.
I thought that was one of the...
I just looked it up online, Randy. It's about 600 kilometers per second is the motion of the Milky Way with respect to the microwave background. So you have to convert that to miles per hour, or miles per second, or whatever.
Say 600 kilometers?
600 kilometers per second, I think it's.
Okay.
Yeah, okay, that's fast.
400 miles per hour.
I have a question. Rich said something about how there was more radiation, cosmic background radiations in certain directions. Does that have anything to do with the expansion of the universe into a certain direction?
It could. Because that's another motion in space that I didn't touch on, and neither did Monty Python, I don't think. You're talking about, first of all, you got the expansion of the universe. You got to think of it in the terms of a framework, you know, the expansion of the universe itself, plus, okay, our galaxy is part of a galaxy cluster, and the Andromeda galaxy is part of that. The galaxy known as M33, which is another one that can be picked up fairly easily in the fall sky with backyard scopes, is part of our local group. The entire group of galaxies is also hurtling in not just our group, not just our what we call the local group. Clusters of galaxies are whizzing off in their own directions too. So,
we need to clarify that a little bit. The universe is expanding, which means that space itself is expanding. But it's not correct, and I'm not sure if you were implying this, it's not correct to say that the space in between the galaxies of our cluster is expanding. Those galaxies are constitute a cluster because they are gravitationally bound to each other. And because they're gravitationally bound to each other, the space between them is not expanding per se, but the space between the galaxy clusters is expanding.
Right. No, that's correct.
To answer Ray's question, no, the universe is not expanding in any one direction. It's expanding in all directions at essentially the same rate. So what that means is that when you look out into the universe from our particular location and you do the appropriate calculations and measurements, you find the galaxy, you find virtually everything except for the stars within our galaxy and the galaxies that are part of our cluster moving away from us, okay? And they're all moving off in different directions, but at essentially pretty much the same rate. It's called the Hubble, I think it's called the Hubble constant, the rate at which which space is actually expanding. But if you were to then take yourself and move, if you could, move yourself even outside of our galaxy to say another galaxy, or if you were just to move yourself to a different position within our own galaxy, and you were to, again, take the observations, make the measurements, you would find that even though you have moved in one direction or another by so much distance, you would still find that everything that you were observing, except for those objects within the cluster that you were in, is still moving away from you at the same speed it was moving away when you were at that other location. So that's one of the reasons why we know there is no, this is hard for people, even I have trouble wrapping my head around it. The idea that we think of space and we think that within any given space, like right here in my living room, for example, if I just confine myself to my living room, there's a center to my living room. But to the universe itself, there is no center. No matter where you move in the universe, even if you were to move out to what appears to be our edge, you would still see that there's probably more universe beyond that. We just can't see it right now because it's over our horizon. And that space would be moving at the same rate as the space where we are now. So there's no central point to the universe, and there's no preferred direction in which the universe is expanding.
I thought the Starship Enterprise visited the center of the Earth in episode. Okay, I do actually have a real question. We always see in Star Trek, the Enterprise hides in nebula, and supposedly it can't be seen. Is that the way a nebula, like, is a nebula really a deep, thick gas that can't be seen through?
No. Possibly parts, but no, they'd be very diffuse. They look like a dense cloud from our viewpoint because it's very far away and very, some of them are
So it's probably like real fog, right? From a distance, fog looks impenetrable, but when you're in a fog, you can generally see where you're going.
Yes, but in a nebula, it would be even more so. Even though that nebula from our distance looks basically opaque, like you can't really see through it, that nebula, let's talk in terms of density, concentration of matter. Inside of a nebula, the concentration of matter would be substantially less per unit of volume than it is even in a mass of fog or in a cloud in the sky. Clouds and fog are more dense, more concentrated, densely concentrated matter than you would find in a nebula in space. And when I say more, I mean much more.
Now, a nebula where stars are being born, okay, in the star, they call them the starburst regions. Yeah, it would be, but it would also be like too hot. You'd melt instantly. You couldn't hide in there. So certain regions of certain nebulas, yes, probably you might be able to hide.
What's the density of a nebula?
They're all different. Like I said, the starburst regions are, you're forming stars. So they're going to be a lot of matter and a lot of energy. Let's put it that way.
So I had a question on like how the years are assigned to whatever. Like someone said 7 or X amount of light years away. Like, what could I search on the web to find out information on how they come to assigning light years to a particular thing?
So it is a measure of distance, obviously. It's the amount that light takes, the amount that light travels in 1 year equals 1 light year. You could look up a lot of good sources on that, I think. But to put things in perspective, the sun is 8 light minutes away. 8 light minutes, okay? So in other words, it takes light 8 minutes to reach us from the source, the sun. So compare that with a light year and you've got an enormous distance. I believe it comes out to something like 5.2 trillion miles.
Yes, or nearly 10 trillion kilometers if you do it in the metric system.
So that's even more than my 5.2 was wrong. So it's probably like 7, because isn't it like 1.6 kilometers to every mile or something like that? So
yeah,
like 7.
Yeah, I think that's it.
7 trillion miles. So it's an enormous distance.
Dale, I have the answer to your question about the density of a nebula.
Yeah.
Okay, listen to this. The density of a nebula and they're not all the same density, but it varies, but there is a range. It vary from 100 to 10,000, from 100 to 10,000 particles per cubic centimeter. Now, a cubic centimeter is small, but by comparison, the Earth's atmosphere is 2.5 times 10 to the 19th particles per cubic centimeter.
Okay.
So a nebula is extremely spread out matter compared to even our atmosphere.
Yeah, I see. Another question for...
I have to go back to DDs for a minute, because that gets quite mechanical. So when you're talking about how did they determine the speed of light, okay, that's one thing. It's like, how is that determined? That's quite a fascinating thing. And actually, a group member, Tim Campbell, did a pretty nice presentation on that. And I may ask him, see if he wants to do something online. So that's square one. Like, how the heck did we figure that out in the first place? It's pretty fascinating. And it was actually kind of figured out by the dawn of the 1900s, as a matter of fact. So then you have the problem of like, well, okay, this object in the sky there, it's we know that it's beyond our galaxy. How the heck did we determine that it's 100 light years away? There you're getting into a whole nother area there, spectrometry and things like that, where we study the spectrum of light of an object, and about roughly 100 years ago, it was determined that all of a sudden, like, wait a minute, the spectrum of an object that's moving away from us shifts to the red end of the spectrum. Very similar to like when you hear a car horn go by and the pitch goes downwards as it's moving away from you. That concept applies to light. So we're starting to get into a lot of, pertaining to your question, there's several different areas of study or whatnot that's going to veer into.
There's a concept called the cosmic distance ladder. That would take a whole hour lecture itself to explain it fully to you. But in essence, what that is, the cosmic distance ladder is that there's a set of different techniques for determining the distance that an object is from you, depending on how far close it is to you. If the object is within a certain distance, we can use its radial motion through space. We can measure that directly. If it's at a greater distance from you, we can't use that. We may use what's called parallax. A simple thing of parallax is if you take and hold your finger out in front of your eyes and then close and then blink your eyes. First, the left, or it doesn't matter which one you start with, but close one eye, look at your finger, and then quickly open that eye and close the other one simultaneously, and you will see, you will perceive
back and forth.
Your finger. That's an example of parallax. And then there are other techniques. Right. Once you get out to great enough distances, then we use what Mark was talking about, which is actually called the Doppler shift. There's a Doppler shift for sound, and there's a Doppler shift for light. And the Doppler shift for light has to do with the changing wavelength of the light as it is either moving towards you or away from you.
So
once it was figured out that an object, oh my gosh, this thing is multiple light years away, it had to be kind of a whoa moment by these scientists who discovered it.
Mark or Randy, does the expansion of the universe cause the microwave background radiation to be redshifted?
Why?
Well, yes, it's not so much as being redshifted as we measure it in terms of its temperature, which is related to somewhat to the red or blue shift. But we find that with some variation, as Rich pointed out earlier, that we find that temperature is around 2.7 to 2.8 Kelvin, no matter in what direction we look out look at out in space from our direction. So it seems to be constant throughout the pretty constant throughout the universe, with some, like I said, some variation.
So the
that redshift, what's happened is that 2.7 or 2.8 Kelvin I'm talking about is just another way of expressing its redshift, if you will, in temperature. Part of the reason it's at that temperature is because the distance at which no, actually that's not true. Just ignore everything I just said. That's wrong. I'll have to research it for you, Dale, and give you a better answer.
Okay. I'll take the question.
Myself, how many miles in a light year?
1 light year is equal to 5.879 times 10 to the 12 miles.
Okay. 5.879 trillion miles. Good old Google, eh? That's a lot of miles. Boy, that's not even so. The nearest star to us is 4 times that. So 4 times 5.8 trillion. It's like, all right. So what is that? 22 point something trillion miles. Talking about some enormous distances. So the only way we're ever going to actually travel to another star is obviously, well, despite all the fanciful science fiction, it would be an unpersoned probe that will take a very, very, very long time to get there. There are a few interesting methods of space travel that are, let's put it that way, hypothetical. Let's put it this way, hypothetical, but very possible. And I forgot his name already. One of the last in-person things last year was a presentation at Independence Library by Bob, and I forgot his last. Boy, I haven't seen anybody for so long. I'm forgetting some people's last names, but he gave a kind of a hypothetical type. He's not a scientist either, like myself, but he researched interstellar travel and the possibilities that could lead to it.
We're not likely to travel, our species or any intelligent life form from this planet is not likely to travel to any other star, even the nearest one, until we have achieved a technology that gets us to a sizable fraction. I mean, a sizable portion of the speed of light. By that, I mean 50% or better the speed of light before we're going to actually be able to master the distances required to go to even the nearest stars. And that's not going to happen very soon.
You don't think we'll drive